So today we are going to start Unit 7. It's the first unit of the second semester. Unit 7 is all about covalent bonding and naming. And okay, hi, how's it going? And so. Yeah, I already had him today, so I have okay, well then just take a nap. Okay. All right. So wherever you can find a chair works for me. So all right. Last semester, we ended by talking about ionic bonding, where we had electrons being transferred. And this semester, we're going to start by talking about covalent bonding, where electrons are actually shared. So, but before we do that, we need to talk about something called electronegativity. Electronegativity is a measure of how attracted an electron in a covalent bond is to an atom in that bond. That's really complicated, but the best way that I can possibly describe it is it's like a handshake. Okay? So like you're shaking somebody's hand, your hand is an electron, their hand is another electron, and when you're shaking their hand, they are participating in a covalent bond. They are sharing that space. So far, so good? So if you're shaking hands with me, right, and I'm clearly like super strong, I have the ability to pull your hand toward me, and you have no choice but to like come along with it. Does that make sense? Kind of. But if I'm shaking hands with somebody like The Rock, I'll do the same thing. I'll just pull him right towards me. Yeah. He looks big, but he's soft. I have a little bit of a man crush on The Rock, so there's that. Now, but the point that I'm trying to make, though, is that when you're shaking hands, you're like sharing space, so you're sharing a bond, okay? But the stronger the element is, the more likely that the electrons in the bond are going to spend time closer to the stronger element, okay? Now, electronegativity on your periodic table, there's always been this number on your periodic table, like, I don't know, right here, that number right there. And that number we've never used before, but that number is an element's electronegativity. So this 1.8 is the electronegativity of iron, okay? And this 3.5 is the electronegativity of oxygen. So in theory, because oxygen has a larger electronegativity, it will attract the electron from iron toward it more than iron could attract the electron from oxygen toward it. Does that make a little bit of sense, hopefully? Maybe, sort of, kind of. So now let's talk about ionic bonds and covalent bonds. In an ionic bond, there are two types of elements, metals and nonmetals. And the electrons in the ionic bond are being transferred. And the electrons are transferred, okay? And the goal of electron transfer is to create a full valence shell or to have 8 valence electrons. In a covalent bond, it's a bond between 2 or more nonmetals, and the electrons are shared. And again, when atoms participate in covalent bonding, their goal is to create a full valence shell or to have 8 valence electrons. So we have ionic bonds and we have covalent bonds. And of course, we can't leave things in chemistry quite that simple. So we have to make them slightly more complicated. So we're going to talk about how covalent bonds are a little bit more complicated right now. Because there's two types of covalent bonds. There is the polar covalent bond, and there is the nonpolar covalent bond. In a polar covalent bond, electrons are shared unequally. That means that in a bond, the two electrons that are participating in that bond are being pulled toward the more electronegative atom more than they're being pulled toward the less electronegative atom. And in a nonpolar covalent bond, the electrons are shared equally, which in theory means that the electrons are being pulled toward each atom in the bond the same. That's what it means in theory. So we have polar covalent and we have nonpolar covalent. Now, this handy-dandy little flowchart here that you should have in your notes is designed to help you process your thinking as you are going ahead. Yes, sir. Okay. Yeah, you can have the homework packet when I'm done with the lesson. Yeah. Okay. So, the first question that you ask yourself in terms of what type of bond am I dealing with is there a metal present? Okay. So if there's a metal that's present, if the answer to that question is yes, you have an ionic bond. If the answer to that question is no, you have a covalent bond. And END is code for something that we call electronegativity difference. So electronegativity difference is a value. And in math class, right, the word difference should tell you to do what mathematical operation? Subtract, right? So if we take two atoms and we calculate their electronegativity difference, and their electronegativity difference is somewhere in the region of 0 to 0.4, then you have a nonpolar covalent bond. If the electronegativity difference is somewhere between 0.5 and greater, you have a polar covalent bond. Okay. Now, we're going to kind of practice this a little bit. So let's start here. And you should still have your periodic table out because that's your chemistry friend. Okay. So I'm going to start with the first two. The elements are sulfur and chlorine. And sulfur happens to be located in column 16 on the periodic table. And chlorine happens to be located in column 17 on the periodic table. So that should immediately tell you that these are both nonmetals. Okay. So the answer to the question, is there a metal present, is no. Now, according to the periodic table, sulfur has an electronegativity value equal to 2.5. And chlorine has an electronegativity value equal to 3.0. So when I go to calculate the electronegativity difference, I take 2.5 minus 3.0, and I put them in the absolute value bars, right? So that means that my answer is going to not be positive or negative. It's just not going to have a sign, right? That's what the absolute value bars mean. So this tells me that it's going to be a 0.5 is my electronegativity difference. So that means it's going to be a polar covalent bond. Now, going back up to my chart, I'll come back to this in a second, but going back up to my chart up here, my electronegativity difference is 0.5 or greater, so that means it's a polar covalent bond. Okay. Now, what are the electrons actually doing? The electrons are being shared unequally and pulled toward chlorine. Because chlorine has a larger electronegativity value than sulfur, and as a result of that, the electrons are being pulled toward the chlorine. So then I go on to my next one, sodium and chlorine. Sodium I know is in column 1 of my periodic table, and chlorine is in column 17 of my periodic table. So that tells me that sodium is a metal and chlorine is a nonmetal. And if I go back up to my handy-dandy chart up here, the question says, is there a metal present? The answer to that question is yes. So that tells me I have an ionic bond. So here, yes, I have a metal. And without having to do any math, I know it's an ionic bond. So I don't need to do the electronegativity difference for an ionic bond. What are the electrons doing here? Well, the electrons are transferred from the metal, which in this case is sodium, to the nonmetal, which in this case is chlorine. Our last example here, we have chlorine and chlorine. Chlorine is in the 17th column, so it makes it a nonmetal on both parts. And chlorine's electronegativity, according to my periodic table, is a 3.0. And there happens to be no metal present, so that tells me that I'm going to go ahead and calculate my electronegativity value. So it's going to be 3.0 minus 3.0, which will be 0.0. And because there's no metal present, I know it's going to be covalent, but it's the type of covalent that happens to be nonpolar. So it's nonpolar covalent. So what are the electrons doing in this one? Well, the electrons are shared equally between both nonmetals. Questions about this? Now, there's something that we need to talk about in terms of that we call dipole arrows and partial charges. Dipole arrows are used when there is a polar covalent bond. And it's a way for us to show the direction that the electrons are being pulled in the polar covalent bond. So in our polar covalent bond, we can show that the electrons are being pulled by drawing an arrow that looks like this. The tip of the arrow is the more negative side. It's also where the electrons in the bond are pulled. And the other side, which kind of looks like it has a little plus on the end of it, is more positive. And that means that the electrons are not spending as much time there. Now, the other way that we can show partial charges is with something that we call the delta symbol. And you may be familiar with the delta symbol at some point in your life or science life, where you saw it look like this. It was a triangle. Well, that was not a good triangle, so it was a triangle. This is uppercase delta, which means change in something. We learned about it in the beginning of the school year when we talked about slope, where it was delta y over delta x, change in y over change in x. But there's another form of the Greek letter delta, which looks something like that, which kind of looks like a musical note. So this is the lowercase delta, which basically means charge. Means some other things too, but if for this situation, it's going to mean charge. So in a bond, the more electronegative element will have a partial negative charge. So we would write delta negative, which means the electrons are pulled toward. They're being pulled toward that atom. Electrons are pulled toward. The less electronegative element will have a delta plus charge, and that would mean that the electrons are pulled away from. So the electrons are being pulled away from that atom. So we have a couple of examples to talk about with that. So here we go. So the first thing I do is I say, okay, what type of elements are present here? Is there a metal present in H and C? And the answer to that question is no. There's a nonmetal. Hydrogen's a nonmetal. Carbon is also a nonmetal. So I go to my handy-dandy periodic table, and I locate the fact that hydrogen's electronegativity is a 2.1, and carbon's electronegativity is a 2.5. Okay, so I'm going to calculate the electronegativity difference. So it's going to be 2.1 minus 2.5. And that comes out to be 0.4. So that tells me that it is a covalent bond, but specifically it is a nonpolar covalent bond. So now if I draw this bond, right, I'm going to simply take my hydrogen, and I'm going to take my carbon, and I'm going to connect them with a line. And that line is an indication that those atoms are bonded together. Now, in this case, because it is a nonpolar, that means that the electrons are being shared equally, and as a result of that, I'm kind of done. I don't have to do much. In the case of the next one, though, carbon is a nonmetal, oxygen is a nonmetal, carbon has an electronegativity value of 2.5. Oxygen has electronegativity value, according to the periodic table, of 3.0. So 2.5 minus 3.0.
It says 3.5.
That's what I meant. Thank you. 3.5, seeing if everybody's paying attention. So it's 2.5 minus 3.5. And that's going to be 1.0. So again, this is going to be a covalent bond because there's no metal present. But specifically, it's going to be a polar covalent bond. So when I go to draw this bond, I'm going to take carbon and I'm going to bond it to oxygen with a line that represents the electrons that are participating in that bond. Now, in this case, because it's polar, I have to tell the world where the electrons are being pulled toward. And because the more electronegative atom is oxygen, my dipole arrow is going to go, that is not an arrow, is going to go like this. But I can also include my dipole, my partial charges. So if the electrons are being pulled toward oxygen, I can do that, delta negative. And if my electrons are being pulled away from carbon toward oxygen, this would be delta positive. Okay. Nitrogen, also a nonmetal. Hydrogen, also a nonmetal. Nitrogen's electronegativity value is 3.0. Hydrogen's electronegativity value is 2.1. So 3.0 minus 2.1 gives me 0.9. And again, there's no metal present, so it's going to be covalent. But because it's a bigger than a 0.5, it's going to be polar. So I'm going to take my nitrogen and I'm going to bond it to a hydrogen. And now I have to figure out, because it's polar, the direction of my dipole arrow. My dipole arrow is going to go toward the more electronegative element, which in this case is nitrogen. So it's going to go like that. I'm going to use my partial charges. So nitrogen is going to have a delta negative charge because nitrogen is more electronegative, and hydrogen is going to have a delta positive charge because the electrons are being pulled away. So that's a brief overview of the differences between ionic, polar covalent, and nonpolar covalent. And so now I want to move on to the next part of this lesson,